Yeah, I would like to really thank the organizers for giving me this opportunity to give this talk online, given that I have a visa issue. So they really did like extra work to make this work out nice. And I also like to thank Juan and Rihua for the very nice introduction and discussion. Yeah, so today I'll be sharing the results that we obtained with I obtained with Eric and Igor and Grisha. And I would like to highlight that we have a very talented and hardworking grad student, Eric Aguielo, who is going to apply for a postdoc this fall. And so uh, keep an eye on him. Upon all of the nice discussion on the motivation of the Yang Li model, I'd like to add one thing, which is if you care about one day studying CFTs in four dimension, I would say like the Ising type theory, which gives us a lot of a lot of success, actually disappear in 4D. And yeah, so the conformal bootstrap, if you just do it naively, just see like kind of like a bound with no features. But the Yang-Li type, which belongs to the I-Phi cube theory, they still remain interesting, and there's some like interacting CFTs in the family. However, if you study them, then you encounter this difficulty that we don't know how to conform a bootstrap, like with a positivity at least, non-unitary CFTs, which is a challenge, and we love challenges as bootstrappers, so we should do it. Okay, so back to the Yang-Li theory, the Yang-Li criticality itself. The strategy that we took to dig it out has two pieces. The first piece is to actually look at the Yang-Li criticality across different dimensions. And we want to really take the 6 minus epsilon expansion seriously. And these days we can find in the literature the 6 minus epsilon expansion computed up to like 5 loops. And actually very, very recently we found another paper talking about the 6 loop expansion just published, which is just published. Um, and it will be very nice. Yeah, well, on the other hand, we also know that in 2 dimension, everything is exact. So it'd be kind of nice to combine these two pieces of information. And we did a two-sided pade, which means we try to find a rational function that matches the analytic behavior near the 6D, agree with the 6 minus epsilon dimension, 6 minus epsilon expansion, and on the other side agrees with the exact result in 2D. So the result that we got, I think it's like a little bit nicer than if you just do the 6 minus epsilon expansion, because you also incorporate the exact solution in 2D. And if you look at the behavior, there's really not that much wiggle room in the middle. Like you can call these some approximation, but like given that they have to be like analytically continued on both sides, I would say they will be like they should be very accurate, maybe up to like the third digit, because everything is like almost linear and very smooth. Yeah, another piece of information that we learned from the 6 minus epsilon expansion is that we should be identifying the uh, TT bar operator to the phi cube operator in more general dimensions. And then there's also another operator, which is the spin 4 uh, primary. And so we call it Q, and Juan call it the C, and Rihua call it X. So yeah, and in this plot, so this plot is a plot of the spectrum in 2D, and here we see that the low-lying uh, primaries are actually very sparse. We only have phi stress tensor, TT bar, which is the phi cube operator, and the spin 4 primary, and everything else is descendant. Okay, and another piece of strategy come from trying to take a closer look at the 2D quantum criticality on the one-dimensional spin chain, and try to learn as much as possible from it. So here I'm showing you our phase diagram in our normalization. So what we do is that we normalize the hopping term to 1, and then take the transverse field in the Ising model parameter, and then take it to be beyond the critical coupling, and then end up at uh, the paramagnetic phase. And then starting from that, we increase um, the the imaginary longitudinal field until we hit the critical point. And along the way of this deformation from the Ising CFT to Yang-Lee CFT, we keep a record of the spectrum that we obtain. And we see that, okay, so there's some, yeah, so what we found, and also later we found also in 3D, that the correspondence between these operators, um, between the operators in Ising and the operators in Yang-Lee, and also the pattern of how the Yang-Lee operators merge as you further, yeah, how these like the patterns of how the Yang-Lee states merge, like the two real eigenvalues merge into a complex conjugate pair. Also, it's yeah. So these information kind of stay stable, and they do not change as we change to different parameters and different dimensions. And this really helped us to try to find what are the corresponding operators across different dimensions. Yeah, for example, we see that T goes to T, I and sigma will, okay, so either I goes to phi, and here later in 3D, we'll find that sigma goes to phi, and then the like identity and phi will be the pair that merge, and T and D square phi is the pair that's gonna merge. And we'll have the TT bar that flows from the Ising's box sigma operator, DD bar sigma, and they merge to box square phi in the like at the critical point, or at the merging point. Um, yeah, so this piece of information is going to help us identify what operators we see are what in 3 dimension. And then we need to also discuss how we find the critical point. We know that as we dial the imaginary the imaginary magnetic field, we will see the mergers, right? But the merging points are not the best place where to identify as the CFT point, because obviously if we try to extract the scaling dimensions, we see a bunch of like exact degeneracies which do not exist, right? So what we do is that we take some other criterions and call the points of that satisfy those criterions the pseudo-critical point, and they vary as we increase the volume size n, the system size n, and then they converge. They should converge to the same thermodynamic critical point in the thermodynamic limit, and as the mergers will do. And here the criterion, so it's really like in 2D things converge really fast, really like you can pretty much do a lot of different things and we'll end up with the same spectrum pretty much. And the criterion we take specifically is the one that requires the dimension of the dimension of the stress tensor to be the space-time dimension 2. And then everything else is fixed by so this criterion also fixes the overall scaling factor, and then all of the other scaling dimensions can be read from a ratio of difference of energy levels. The last piece of information we took from 2D is that so really benefit a lot if we take the longitudinal field, or sorry, the transverse field of Ising model to be like way beyond the critical point. So we're deep in the paramagnetic phase, which is kind of so I think the naive understanding is that we get like as far as way as possible the Ising critical point, so the RG flow is kind of faster. Yeah. So they're using this parameter, so the 1 over n correction seems to be the smallest. Yeah. So now let's take some of these information to 3 dimension and try to study them. First, let's see, okay, so uh, let's see the phase diagram, which is pretty much the same. So the Hamiltonian is introduced by Yuan. We have pretty much the fuzzy sphere using Hamiltonian plus a z dimension, a z density term in the fuzzy sphere. Um, yeah, and so there's also this hx parameter, which we take to be above the critical point so that we are in the paramagnetic phase. And then at some large hx, we turn on the z coupling and then tune it all the way to the Young-Lee criticality. So here's an example of the spectrum that we obtain from this trajectory. And we see the same kind of pattern, right? So out of all of these uh, matching and mergers, uh, remarkably, we see that here box sigma is identified with phi cube operator, and the box square phi merges with it. Exactly the same pattern as in 2D. And also, like we'll see, the spin 4 tensor also spin 4 tensor of Ising goes to the spin 4 tensor of Yang-Li. Stress tensor of Ising goes to stress tensor of Yang-Li. So everything is expected, same pattern. Uh, okay, so now let's talk about the criterions that we use to identify the pseudo-critical point at finite n. So it's really bad to use okay, so first it's a self-consistency check that we get the same thermodynamic critical point using different criterions. We can see how the merger changes as we increase the volume. We can see how the stress tensor is equal to 3 criterion moves the critical point, and also how the finite size scaling, meaning that the gap should go as 1 over the 1 over r, pretty much. So all 3 criterions converge to roughly the same critical point up to some numerical precision at finite size. So this really gives us the confidence that we're finding a consistent CFT or a consistent critical point. Yeah. And also, as is discussed in Juan's introduction, here we have a line of CFTs, which means we should get like equivalent spectrum or exactly the same CFT spectrum up to some overall normalization for all the points on this critical line. And we tested that this is true. So I'm getting a little bit ahead of myself about like how we treated the finite size scaling. But roughly, we could see that no matter how large or how small that we take this longitudinal field, sorry, the transfer field easing in the easing, or in other words, how deep we are in the paramagnetic phase, we always get the same information, the same CFD data as we go to the corresponding Young-Lee fixed point. Yeah. So now let's talk about how we treated the scaling dimension at the finite size scaling of the scaling dimensions. So here I will present a very, very humble way of using the conformal perturbation theory, or not trying to like do an overall fit that tries to like correct some of the finite size error. Instead, we're just trying to use this as an argument to see like what is the leading power of convergence. So from these two works, we have a formula for the energy eigenvalues as the scaling dimension of the CFT plus some relevant and irrelevant corrections, which grows or fall off as the volume increases. And here the volume is proportional to the number of fermions n. And if we plug in our criterion, the main one that we use is the stress tensor is equal to the dimension of the stress tensor is equal to the space-time dimension 3. We'll see that we're able to eliminate the relevant power, which grows with the system size, and we're left with the correction from the leading irrelevant contribution. And from the pattern from the spectrum, we see that okay, so from the 6 minus epsilon expansion, which gave us uh, the scaling dimension of the phi cube operator, which is roughly 4.6, and that one should be the leading one. If we plug that in, we can estimate the leading error fall off as 1 over n to the 0.8. So we use that piece of information in our fit. And beyond that, we also so there will be like some further higher order, like higher dimensional operator and higher order in the perturbation theory, which is a very complicated story. So we just decided to be agnostic about those and try to just expand them in just regular series of 1 over square root of n. Uh, and then we can roughly test the stability of our fit, which is not much. They wiggle a little bit in the third digit in the delta phi. So then we perform this type of analysis to every single eigenvalues that we can resolve. Remarkably, we see that most of these descendant operators, they could have like various different size of finite size finite size error. But once you do this fit, they all converge to like almost exactly integers from the corresponding primaries. Uh, and then that gives us the right plot. So we see, okay, so this plot is a plot of the spectrum after we do this kind of fit. Here we can identify 4 primaries, phi, stress tensor, phi cube operator, and this four dimension the spin 4 primary Q, which from the look of this plot, you can see that this operator might have a little bit more error. But our determinant, we can roughly say that the scaling dimension is around 4.9. Yeah, and everybody else is a descendant, and their scaling dimension agrees with the conformal symmetry, which is very nice and gave us confidence. Uh, and we also tried looking at the OPE coefficient, which is, so this paper gave us the method as using the fuzzy sphere operators. So if we take some density operators in the fuzzy sphere, in the thermodynamic limit, they should flow to the most leading operators uh, in the CFT with plus correction from descendants or higher up primaries. And then we wrap them with some smearing against uh, uh, some spherical harmonic basis functions in order to project to a certain primary certain scalar operators. And then from the state operator correspondence, we also know that the eigenstates correspond to CFT local operators. So what we study will be a matrix element of the eigenstate and these fuzzy sphere operators, and identify them with the 3-point functions in the CFT, which give us the OP coefficient. So from these 3 examples of scalar OP coefficients, we see that they converge pretty well. There is some error that we believe should be at the third digit. We have consistency from using different operators which flow to the same CFT, different operators on the fuzzy sphere which flow to the same operator in the CFT. Roughly, the leading error come from d squared phi descendant. There will be more subleading ones, but it's going to be a complicated story. Then we try the linear, and this correction should give us 1 over n error. And we also tried quadratic fit, and that gives us roughly an idea of like how much the error is. Remarkably, the C555 agrees with the Glalzi result of a conformal bootstrap. Yeah, so and then we can try a little bit of doing the digging out the spinning uh, 3-point functions or the OPE of spinning operators. The 3-point functions of spinning operators here specifically, we tried spin scalar 3-point functions, and they come in different polarizations. Uh, which is summarized here. Uh, and then so if you wrap the fuzzy sphere operators using different um, spherical harmonic basis, you actually get access to different polarizations, and it's a very nice uh, exercise to work out the exact correspondence between these 3-point functions and the matrix elements in generic CFTs. Once we work them out, we can just do the calculation and make some plots for the phi tt 3-point function for different polarizations. And here we have some nice structure from the nice input from the CFT side. The stress tensor is a conserved current. So the conservation condition gives us additional constraints between the three OPE coefficients. So actually, there's only one independent guy, and then the other two guys can be calculated from the independent one. And we see that although the higher polarization ones converge kind of slower and slower, but qualitatively they're converging towards the expectation from the conservation condition of the CFT, which is another consistency check. Yeah, so yeah, there's also an interesting story that we like interesting discovery that we had in doing these 3-point functions in Yang-Lee CFT. We found that okay, so there's a lot of things that we can there's a lot of CFT consistencies that we can check because there are so few parameters and it's overdetermined. There are many different ways in fuzzy sphere to calculate the same quantities in the CFT. And for example, if we look at the 3-point function of descendants of phi, involving the descendants of phi, uh, they should be um, they're completely fixed uh, using the conformal algebra. So I'm taking as the yeah, so I'm taking this result from these two papers of conformal perturbation theory. So if you take, for example, the d phi phi 3-point function, it's related to the phi 3-point function by some factors that contains the dependence of delta phi. And you can reverse the logic. I can calculate d phi and phi on fuzzy sphere, and the ratio is going to tell us something about yeah, we can use this ratio to actually fix the scaling dimension of phi, and we tried that, and this we obtained the red and the blue curve in this left plot. And you can see that while the eigenvalues converge with seemingly something like a very small power, so there presumably is going to be more finite size error. The 3-point function determination actually seems to converge like much faster. Uh, So this is like a kind of a surprise, also like a very nice consistency check uh, of the conformal symmetry. So then, like wrapping everything in 3D, we use the different methods. Well, we use the different methods in fuzzy sphere to obtain the scaling dimension and OP coefficient for the leading few primaries. And we can compare them with our previously determined two-sided Pade and some of the previous results we found from the literature. We see that they are uh, like, yeah, they actually agree pretty well. So delta phi now we can be very confident that it should be like something around like 0.2145-ish. Um, and also like the C555 agrees very well with the truncated bootstrap. And our result, yeah, so from the fuzzy sphere, since we studied very carefully, I think we have like a better precision uh, than some of these previous determinations. And we can improve them, hopefully, using DMRG or more smart setup of the quantum criticality. Before I end, I'd like to also mention that in order to achieve real quantization, one way is to use the fuzzy sphere, which gives us exact SO3 symmetry, but sacrifice the locality a little bit. It's a very nice model. Um, and on the other hand, we can also just use a explicit geometry, but tessellate the sphere and get the polyhedron, and then actually realize the explicit lattice model on polyhedron. And in order to preserve SO3 symmetry as much as possible, we would like to study the regular polyhedrons, which are pioneered by these works. Um, the downside is that SO3 is inevitably broken, and also there are only finite number of regular polyhedrons in each spacetime dimension. But we can still study these models as an approximation, and we tried it on, so for 3D, we tried it on cube, icosahedron, and dodecahedron using exactly the same strategy as I discussed before, and we found a consistent result. The scaling dimension of phi on cube, icosahedron, and dodecahedron at large hx and hz tuned to the critical point gave us something that's consistent with what we found, and seems that the dodecahedron is like pretty accurate. And we also, yeah, see the same pattern of operator flow from Ising to Yang-Li, and the same merger from like Yang-Li to like the same merger of the Yang-Li criticality. And then after we got some experience in studying the criticality in 3D, we can also try to study the regular polyhedron in 4D. And here we tried the 24 cell, which is okay. So I'm trying to not get too much details, just to say that this is a regular polyhedron that preserves the SO4 symmetry as much as possible, and it has 24 cells. And beyond that, there's like a 120 cell and 600 cell, which is obviously beyond our scope. And we see that, okay, so here the flow pattern and the merger pattern really helped us digging out what operators are what, because we have less symmetries. But long story short, we obtained delta phi and delta phi cube among some descendant levels. And we can determine delta phi that is pretty close to the two-sided Pade, which should be more accurate than three-dimension because it's closer to the six minus, close to six dimension where everything is perturbative, right? So here, delta phi is like 0.02 and delta phi cube is like 0.4. And then the scaling dimension of the descendants are related to the corresponding primaries at roughly like 0.3, 0.4-ish. error. So we get like reasonably good approximation without doing any finite size scaling. So if there's a world in which we can do finite size scaling, I would expect we can also obtain these scaling dimensions quite accurately. So that brings us bring me to the outlook. So first, to conclude, we obtained numerical solution to the quantum Young-Lee criticality in various dimensions, and they all agree to the 6 minus epsilon expansion and conformal symmetry. So in one word, it worked. So to move forward, we can try to consider more of these phi cube family. So phi cube is actually a very large family, and you can study them first in the 2 dimension as the non-unitary uh, um, minimal models. And then a lot of them have Ginzburg-Landau description, and which allows you to continue them to higher dimensions. So for example, the M38 in 2 dimension has a Ginzburg-Landau description of 2 scalars with imaginary cubic couplings. So we might like one day have like archipelago of phi cube theories, for example. And it will be also very nice to combine fuzzy sphere and bootstrap study. Um, so without positivity, the best we can do is to truncate the crossing equations using the Gliozzi method and obtain approximate solution of this truncated crossing equation. And there, since it's not rigorous, we really want to guide the solution using some heuristic guess that has some precision. And luckily, fuzzy sphere can actually provide us a lot of these initial input. Or we could try to figure out how to use positivity in the open system. It's not that there's no positivity, and in fact, the lattice models in that is governed by the Lindblad equation can actually be bootstrapped using the positivity condition. We just don't know how to conformal bootstrap using the positivity uh, of the open systems. So it remains an open question. Is actually a good opportunity because it has to work in some sense. Finally, the fact that the 24 cell, even the 24 cell gives us a very gives us reasonable accuracy for 4D Young-Lee is very encouraging. So if there's a generalization of the fuzzy sphere in 4D, we should be able to do the finite size scaling and obtain pretty good results for the 4D interacting CFT. Uh, okay, so that's all I wanted to share. Thank you very much.
Thanks very much, Yuan. It was a very nice talk. So, is there any question? Yeah, here's some question.
So how about 5D? It's very easy to generalize fuzzy fit Sophia to 5D. So just wondering if you guys think about that.
We haven't tried it just because like the lattice is like a yeah. So we've basically been thinking about the lattice, and the 5D lattice is probably a mess. But yeah, sure, we should be able to do 5D using a fuzzy sphere like setup. We haven't done it, and the good part is that it should be okay. So the good part is the analytical solution or the 6 minus epsilon. Prediction should be very, very accurate because it's so close to 60. The downside may be like the finite size scaling is a bit hard to work out because it's very high dimensional. So yeah, I think this is a very good thing to work on. Yeah.
Okay, so I have another question is that you talk about this flow of those operators as well as how operators merge. I'm wondering whether that's a universal statement or it's like model dependent statement. If you change some models, then you will get different patterns.
I think we'll get different patterns. So like this is like obviously model dependent. It's just well actually, so I'll say like probably within this universality of like Yang-Lee to Ising to Yang-Lee flow, we'll get like more or less the same flow. But I'll say like nothing is rigorous and things might change. For example, in 3D, we have identity that's below the phi operator. But in 2D, identity is actually above the phi. Uh, just because like yeah, so basically there's like it's not a rigorous statement. So yeah, there could be some model dependence, but it's very stable. It's really helpful. Yeah.
Thanks.
Other questions?
Hi, thank you for a very nice talk. I had a question about your criticality condition. So you're fixing some ratio of that's supposed to flow to the scaling dimension of t to 3, and then you were saying that the relevant uh, parameter is tuned away,
Yeah.
but you're setting the ratio exactly to 3, and you have some irrelevant terms in your action. So I'm wondering how you can say that only the relevant term is turned off.
Yeah. So you can actually just like plug this in to this equation. And what you get is that you can solve G phi as some function of G phi q. And then G phi, well, so in order for this to be true, you have to have like the matching. So basically G phi will be like down by 1 over n to this power. And then this, when you plug it in, this will give the G phi term the same, roughly the same size as G phi cube term. So in that sense, I'm saying that the relevant power, which is growing as we increase the volume size, goes away.
So you're trying to cancel a growing power with a decaying power. I mean, maybe this works for finite range of n.
Yeah. So it's just that when you're a little bit away from the critical point, but your deviation is down by some power in the system size, then you can expect that if that power is small enough, then you can still flow to the same CFT. If you deform by say something order 1, then of course you will flow to something different. Yeah.
Okay, thank you.
Just a curiosity, so the epsilon expansion series is Borel summable? Is that known? Or the radius of convergence of the Borel transform is known? Or
I think it is. At least it gives us a very good results. Yeah. But I don't really know the underlying theory of Borel resumability. Uh, yeah, but
because
people have
for the
tried it.
radius of convergence of the Borel transform, maybe you can do a bit more refined than the Pade. There are some techniques, but yeah.
Yeah. Thank you.
This M38 theory you mentioned in the end, does it have the pulse symmetry or somehow? Which symmetry does it have?
I don't remember on top of my head. But I think it has a Z2. Yeah. So they're basically a coupling of so it's basically
I'm
two
asking is
units,
that
sigma and phi. So there's a yeah.
okay, the reason I'm asking is because the pulse model in format epsilon you have the PT symmetry, but the 2D pulse model do not have it. I'm wondering whether what should that become in 2D? Is this M38 or not?
You're trying to sorry, you're trying to identify pause with M38 or
Yes, I guess you already answered me because it's the symmetry does not match. So thank you.
thanks.
So do you have any speculation or any explanation for why the method of determining OP coefficients, no, scaling dimension using the 3-point functions worked so well?
So basically, the idea is that you can study what's the correct what are the leading corrections to this 3-point function. So as we know that is contaminated by its own descendants and also higher primaries. So its own descendant. So we have like d phi, d square phi, all of these operators. So if we smear this d phi with phi with the I think if we integrate a total derivative on the sphere, or spatial total derivative on the sphere, it should just vanish, right? So in that sense, we should not actually have, say, like Laplacian phi type of operator. So the total derivative can only be acted on the time direction, right? But
What
then,
correction
yeah.
from the relevant? So the main correction for the eigenvalue method is the correction from the irrelevant operator that you don't tune away. And so why, the phi cube,
Oh, yeah, yeah.
so
Oh,
why this phi cube in the which is perturbs the Hamiltonian and it perturbs the eigenvalues. So why doesn't it perturb the other two curves?
no, I think the critical point converges to like, okay, so the eigenvalues converge slower because you're basically comparing the scaling dimensions of, say, phi cube to three. But like actually the critical point converges to like what should I say? You actually the critical point converges with like I think delta phi minus delta phi cube, which is like something around three, right? So then we should say that we're right on top of the CFT, just with some irrelevant corrections. And
Same
yeah,
PowerPoint.
it's not obvious to me how these irrelevant perturbation of the Hamiltonian enter the three-point function. Yeah.
Okay.
Uh, yeah, maybe that's a caveat. I just don't know. But just from the analysis of how these total derivative enter, we can see that they cancel out in this ratio. And that's why that there's like a very flat uh type of
Okay.
like, yeah,
Yeah.
finite size.
Nice observation. Okay, last question by Antonio.
So for this Platonic solid discretization, icosahedron and so on,
Yeah.
what is the exact role of these discrete symmetries of SO3? Like, if I just pick a random discretization of the sphere, why will I just mess up?
Then you won't be able to say anything about spin, right? So your operators, okay, so basically uh like the different polarization of the same spinning operator is going to be scattered everywhere, having different 1 over n corrections. So you have like a very messy spectrum. And even if you have some series that converge to the same CFT, it's going to be really difficult without these finite group symmetry uh, in
Thanks.
order to figure out the scaling dimensions.
Okay, thanks a lot again, Yuan, again for the talk. That's yeah.